Welcome to Complexity Made Simple, and welcome to the latest video in the Catapult case study. Now, before we get on and look at the learning points from the process flow cause and effect analysis in this video, what we're going to do, of course, is we're just going to update the project presentation. So let's just remind ourselves where we've got to. We ran the process 25 times in order to get the current state of the physics of the process. The state of the physics was that we had too much variability. Because we had too much variability, there was a good chance that measurement system was part of the problem, and we could definitely see in the exercise it was very difficult to see where the ball lands in this process. So we've conducted measurement system analysis. We have a measurement system problem, and we know we're going to have to improve the measurement system, which of course we do in the improve phase of this project. We then went into the process analysis phase, process flow, cause and effect. We've put that in the presentation. Here's the flow diagram, here's the cause and effect diagram, and from the cause and effect diagram we've then done a control plan, and that's the improve phase of this Catapult case study. And then we fired the process again, and we're getting a much more stable process. Only a 5-inch range now instead of a 43-inch range. So now let's get on to some important learning points from the process analysis phase of this project. Okay, now we're going to summarize up the learning points from the Catapult exercise. We're on slide 32 now, and you can see I've got a nice blank page for you there. The reason being, this is super important that you get some notes down on the learning points from this exercise. Now this exercise, when I was going to do this online, this is the one exercise that I look and go, I want to do this live. I can't reinforce how important the learning is from this exercise. It is the centerpiece of Six Sigma. It is the centerpiece of your projects. So learning the principles from this game is super important. So we're going to do two things. I want you to make some notes. We're going to first of all talk about some things that we didn't do in order to solve the problem with that particular piece of equipment. And then we're going to talk about 4 process thinking principles. That's what I call it, process thinking. I'm going to give you 4 principles that I want you to learn, take on board, and use them every day. But the first thing we're going to do, we're going to talk about 5 things that we didn't do in solving that problem. So here we go. So here's the learning from the Catapult exercise. And as I say, I wish you'd have done it live, but it wasn't possible. So point 1, did we blame one thing? Now, you know, people come and work with you on problem solving courses and all sorts of things, and of course the consultants, they like to talk about finding the root cause. Now, of course, finding the root cause suggests, of course, that you're looking for that one golden nugget of something that's changed in your process, that if you put it right, everything's right with the world. Now, we didn't blame one thing, it was multiple things. Okay, now this first learning point here, this goes to the heart of what we talked about earlier: chaos, control, excellence. This process was in a state of chaos. when we were firing the catapult, we were getting this wild, unpredictable result. Maybe over 20 inches on the range. By the way, for the same setting. So we fired that catapult with the same setting, and we just let everybody play with the catapult, and we still got a range. I mean, sometimes I do this. I get a range in some of the exercises of 100 inches for the same setting. So the process is in chaos. And what chaos means is it is multi-causal. In SPC phrase, they would talk about it being common causes. Lots of them. All right? So it's multi-causal. There is no point looking for the root cause here. If all you did was put a stop at the back to make the angle work better, it'd improve. But the variability wouldn't go away. It wouldn't be world class. It wouldn't be a world class process. Now, we did loads of things. We stabilized the catapult. We come up with a standard operating procedure for loading. We come up with a stop at the back. We come up with a better way of measuring where the ball landed. Multi-causal. Okay, and so we didn't blame one thing because the process was in chaos. Had the process been in control and that had have happened, well, that's going to have a root cause. That's going to have a root cause. Think about it. Your process is in control. Everything's locked down and you've got it all working brilliantly. What's the chance that all the controls would all disappear all on the same day? They'd all break all on the same day. It's not going to happen, is it? So if you've got control and the control goes crazy, that'll have a root cause. It'll have the one thing. The first thing's gone. The first thing's broken. The first rule has been violated. Here, there ain't any rules. So we didn't blame one thing. That's really important. Everybody's looking for root cause. Everybody's saying, I know what it is, I know what it is, I know what it is. No. When you've got chaos, it's multi-causal. Okay, that's learning point number one. Learning point number two, so write these down, folks. Learning point number two, let's have a look. Did we adjust? Did we adjust the process? Did we go, oh, I know what we'll do, we'll buy it off. When I get a low one, I'll pull the angle back a little bit further, make it go back to where I want it to go. If you think about it, did we adjust? If you think about the catapult, on the catapult, there are 5 adjustments. The angle, the pin position at the front, the stop angle, the elastic position at the back, and the cup position at the back. 5 adjustments that we could make. None of those 5 things changed. Now, you already found 10 variables. If I'd have allowed you to adjust the settings, you'd have had 5 more variables. Would the process have been getting better or worse? Process would have been getting worse. Adjustment is a really bad idea. And I know you do this. I've spoke to people about plant that you run. I think the steel making process, you like to do this a lot. Change the change the kind of the chemistry, etc. It is a really bad idea. The more you fix things, the better the process will work. We'll come back to adjustment a little bit later, but did we adjust? No. What else didn't we do? Did we take the machine apart? Did we take the machine apart? Now, if we're not letting technical people adjust the process, we're often letting technical people take the bloody machines to bits. Now, a bit more difficult maybe in your environments. You know, sometimes it's very easy to take the machine apart, get a tool maker, tool setter, that in there, and they got the machine in bits. Did we take the machine apart? Was there anything wrong with the Catapult? No, we didn't do this. Was there anything wrong with the Catapult? No. So we didn't take the machine to pieces. There's nothing wrong with it. Okay. What's the next one? Here's the next one. Did we have a target? Did we have a target? So did I ask you to hit, I don't know, 67 inches, 123 inches? Do we have a specific place to land? Well, no, we did have a target in the exercise, and the target was to reduce the range. So all I wanted you to do was to take this 20-inch range and make it as tight as you possibly can. Your target was to remove variability. I didn't care where you landed. I just wanted you to land in the same spot for the same setting every time. Chaos, control. You see, that's control. Removing variability is control. Now we can work on excellence, which is landing where you want to be. So did we have a target? No. Because in order to be able to move to a target, you've got to know where you are. So where were you? Where were we in the first round? Well, we were all over the place. So if I ask you to adjust a machine from all over the place to hit a target, what adjustment would you make? Makes no sense. Now that you're hitting the same spot for the same setting, how long do you think it would take to maybe hit a target which is 10 inches longer, or maybe 8 inches shorter? Yeah, simple adjustment. Be very easy. How long do you think it would take you to hit a target here? It would take you forever. By the way, if that's what you're trying to do currently in the plant, you're trying to hit targets when you haven't got control, is it taking you forever by any chance? Because it probably is. Yeah, so did we have a target? No. And finally, did we have an inquest? Now, when I worked for Sony, we used to have inquests every day. I look back on that time, and despite the fact that there were some great things going on at Sony, there was some, things where, maybe we wasted our time quite a lot. Having an inquest is getting a defect in your hand. So you get the dead ones in your hand, and you look at them, and an expert tries to figure out what went wrong. They go, oh, look at that. I know what's wrong here. We haven't set the winky valve right on the back of the machine. Yeah, and so you try to figure out, using the expert knowledge, why that defect has happened. Now, in this instance, it would be like taking the tall ones, the high ones, and going, what happened there? Don't forget, it's multi-causal. So when you say what happened there, you haven't got a clue what happened there, because everything changed. And then you go, oh, we'll take the low one, and we'll ask the low, because this might be, a defect above the top tolerance, a defect below the bottom tolerance. So we'll get the dead ones in our hands, and we'll try and figure out, what's the root cause of that? Well, when everything's changing, there ain't no root cause. So the idea of looking at this is a function of all the other results. The fact that this is just all the variables in one direction. This is just all the variables in one direction. This one here is suffering from all the variables as well. They just happen to be set in a middle position when you get average results. But the lack of control is what's killing you. Okay, so Did we blame one thing? Did we adjust? Did we take the machine apart? Did we have a target? Did we have an inquest? Now, the reason why I use this list of five, these 5 learning points, is because these are behaviours that most companies have, and what they find is, despite their best efforts, the problem keeps coming back again and again and again. And it's because you are in chaos when you need to be in control. Now let's clean the whiteboard off, get some room, and then I'll show you the 4 process principles that are crucial to problem solving and being world-class technical problem solvers. Let's clean the board and we'll look at these 4 principles. Okay, let's get these 4 process thinking principles on the board. Now, when we got to the last thing on the list there that you didn't do, I said you didn't have an inquest. You didn't spend time trying to inspect the defects. The point about having an inquest is you're looking at the outputs. You're looking at the finished product and you're trying to guess what happens in the process. So what we're not going to do, in the exercise you didn't do this. You didn't look at the outputs. You didn't stare at the product. What you looked at was the inputs, because here's the biggest thing I've ever learned. Once you know this and you use this, you can fix anything. Because inputs control the outputs. What you did in that exercise was you identified all the inputs. Now, I also told you to call them variables, which they were, but they were input variables to the process. We identified the inputs, we fixed the inputs, we made all the inputs stable, and when all the inputs are stable, the output's got to be stable. Inputs control the outputs. It's the simplest thing to state. It's a law of physics. Providing the laws of physics are working in your plant, you apply that thing, good things are going to happen to your process. So inputs control the outputs. Now, what was it about the inputs that we were most interested in? We were interested in their variability. Because if this first point is true, this has to be true. The variation in equals variation out. You cannot buy variability off with more variability. So if you have a piece of equipment, you have your process here, your money-making process. You have input 1, you have input 2, and you decide. Input 1 is varying. So in order to stop that, of course, what's he doing over here, by the way? It's making your output vary. So input 1 is varying. So what do? You move input 2 to try and buy that off and to make this go away. Now what have you got? Well, now you've got 2 variables moving. Guess what you get instead? You get double bubble. You've just made the whole situation worse. You cannot buy variability off. And I know you tried to do this in the blast. I think you look at the iron ore coming in and you assess its chemical properties. Then you make changes to the recipe going into the blast. And I think you do the same thing in the steel plant. You're making it worse. Fix the variables. Decide what the rules are for the variables you can control. Fix them and see what happens. Here's what's happening in most companies. Most companies are doing this. I mean, I only put 2 variables here. What they have is this. They have, let's say you have 5 variables. We'll give them letters, keep it simple. A, B, C, D, E. A is raw material, and you dig it out of the ground. And it goes up and down like that. Your product has varying performance, okay? What you do is this. In order to buy this off, you allow B to move, C to move, D to move, and E to move. And when somebody asks you, what's the root cause of that? You blame it all on A. You go, it's the raw material. You got 4 other variables moving. Why aren't they the problem? All of those 5 combine to make that disaster. And what I want you to do is to fix the 4 that are in your gift. Because if you fix those 4, then you see what happens. Then you can assign that to the raw material. But until you fix the other variables, you can't blame your bad behavior of your plant on one variable when every bloody variable moves, and you certainly cannot buy it off. Doing this to a process is a super bad thing to do. So variation in equals variation out. Fix the variables in your gift, ignore the variables outside your gift. It's going to be a very dispiriting discussion to talk about things you can't control. So that's the second principle. The third principle, variation first, targets second. Let me get a bit more space on this whiteboard and I'll explain this one to you. Okay, variation first, target second. Now we looked at this earlier. Unless you're somewhere consistent, it's impossible to adjust to somewhere new because you don't know where you are. If you don't know where you are, how can you adjust? So you've got to get control of the process first. So that's reason 1. Reason 1 why we want you to get rid of variability, want to get rid of this chaos, is so you know where you are. And then when you know where you are, then you can hit the target. So that's reason 1 why we want you to follow this principle. Reason 2 then is what variability does to your understanding of the process. When you've got a very chaotic process, when would you take action? Let's say this is defects. So the high graph is bad news, the low graph is good news. When would you typically jump up and down and want to take action? Well, usually, of course, you'd want to take action on the worst ever performing day. Now, think about this. All of your variables on the worst day, all of your variables are all in one direction. If you decide to do nothing here, what do you think is going to happen anyway? Do you think all your variables, you haven't got control, so do you think all your variables will stay in that bad condition? No. What's going to happen is the process is going to get better anyway, whether you do anything to it or not. But of course, you don't do nothing. You take action. So, I don't know, technician turns up and he gets the Allen keys out and he starts fiddling with the machine. And he just talks to it nicely and whispers a magic spell. And then of course in the morning, what does he notice? Well, in the morning, he notices that the process got better. What do they think? I did that. Bloody hell. I've been working here for 20 years. I know what's going on. I did that. Did they do it? It was going to get better anyway, because you don't have control. You weren't going to get this consistently bad. You haven't got consistency in anything when you've got chaos. That's what variability is about, chaos. Now, I'm not getting at the engineers here. Yeah, so guy adjusted the machine and he thinks he's put a solution in. This could be that's what I think. This could be the senior manager. He thinks, sees the bad performance and he thinks, well, what's going on? He bounces onto the shop floor and the first two guys he sees, he gives them both barrels. Next day, what does he notice? Process got better. What does he think? He thinks he did that. Of course, when does he do it again, by the way? Same with the technician here. When do you call him out again? Well, you take action here, didn't you? So either the guy gets his Allen keys out or the senior manager shouts at everybody again and the process improves again. Now everybody's convinced. Getting the Allen keys out is the solution. Now, shouting at the shift is the solution. What else could you have here? This could be raw material. Somebody decides this is the batch of raw material, so what do? They change the batch of raw material here. Next day, what do they notice? They notice the performance got better. What do they do when they get another peak? Well, they do it again and the performance gets better again. Now they're convinced it's the raw material. And if you sit these three characters down and you get them in a problem-solving meeting and you say, what do you think's wrong with this machine? Somebody goes, well, we're not setting the machine up properly. The manager goes, well, we haven't got the discipline of the people, they're not taking proper care over the process. The team leaders go, no, it's the raw material, it's the raw material. I've got the data to prove it. And by the way, they've all got the data to prove that they're correct. That is what variation does to you. It will drive you absolutely crazy. You will never solve a problem as long as you have two holes in your head. He said something else then. As long as you have holes in your head, you're never going to solve a problem like that. You've got to get rid of the variability. So inputs control outputs, variation in equals variation out. It's got to be variation first. Otherwise we'll get spurious knowledge about our process. It's got to be variation first and targets second. And the fourth principle is you have to work on the process, not the product. We get obsessed with the product because the customer wants the product. The customer looks at the product, they evaluate it and decide it's good or bad, and we tend to do the same. If you want the product to be good, you need to work on the process that created it. How do you define the process that created it? From the inputs that go into it and how well you control them. Now the exercise you just did, even an exercise that was done essentially electronically, you did it from afar, you just improved that catapult process and you used those four principles. The idea of those four principles is that what I'm giving you is process thinking. And when you have process thinking embedded in the way you work, you can solve any technical problem that's put in front of you. Process thinking, there are the four principles. Eat and sleep these 4 principles, please. They are the most important thing in the course. Okay, so it's really important to remember those 5 learning points and those 4 principles. Those 4 principles are just in every piece of physics in your company. They're in lean implementation, they're in Six Sigma implementation. So the 4 principles are really important. Write them down, learn them every day, really internalize those principles. Now the next video that we're going to release next week, that's going to be some additional advice on how to do process flow, cause and effect in a real world situation. The Catapult is a little bit of it's a great game to play. It makes the point about physics, but it isn't quite the reality of what your manufacturing site looks like. So in the next video, we're going to give you some great advice about what process flow, cause and effect would look like, and how to enhance the cause and effect diagram for the reality of the situation. I'll see you next week.